In the last video, we started to look at volcanoes and how we can use the new steam turbine to get some power out of this super hot metal and cool it down to a useful temperature so that we can extract it and use it throughout our base. Now, I gave you guys the challenge of how we could potentially optimize this, and you guys delivered 1,000 ideas. So welcome back, my fellow duplicants, to Oxygen Not Included. Today we're going to optimize the volcano and how we can get some of that energy out via the steam turbine. Now, since there are so many comments, over 100 and something there, I had to put it into a flowchart. So this is what we currently have here. There's two different thoughts, right? We have a vacuum chamber over here on the left so that none of the heat interacts with the environment around it. And we only rely on that physical contact between the metal or whatever it is onto the tiles down there. The other school of thought is to have something over the top of a volcano. We've done that several times before, so that we're simply drawing the power off of that. But how can we potentially keep the temperature in an environment like that cold enough so that we don't need to have space age materials for the auto sweeper and loader and everything up there? Because you could imagine that over there, with stuff being kicked out at over 2,000 degrees Celsius, will get very, very hot. Now, because this is such a complex topic, I'm going to split this into two parts here. So today we're going to focus over here on the vacuum system, and that has a lot to do with the thermal conductivity and how we control that in a vacuum environment. The system over here on the right, the enclosed system, has a lot to do with mass, how much energy we're putting into that mass, and how much energy we're taking out of it. So there are two different schools of thoughts. We can make either of them work, but for the sake of focusing, we're going to do one at a time. So today, this is what we're going to focus on. Now, you guys delivered a lot of great ideas, such as maybe adding thermal shift plates to a tank of liquid that has a large enough mass to where it isn't going to flash over. However, I think the way that this game actually works, you're potentially always going to make some gas because it's just going to flash at that very first moment. It doesn't necessarily interact with all of the liquid to begin with. One thing that was talked about a lot in the comment section here was making the distance between our heat source and the steam turbine shorter. What this does for us is it allows us to draw power faster, so how much heat can we remove per cycle should be greater than the heat that is added to the system, or at least in theory, what we can do in a given amount of time should be greater. Does that really matter if we are automating how and when we take that metal out? Not necessarily, but it does give us an opportunity to A, make the whole thing smaller, and B, potentially get that heat out faster. There were several comments talking about the doors that we're using here, such as an additional one to increase the thermal transfer into the steam chamber, and other ideas such as a ladder door to either move that material down or to the side as it cools and whatnot, so that we don't have all that mass in the same spot, which is pretty clever. Along that same idea is to use the actual conveyor from an auto sweeper to ship iron around on rails to transfer heat. Interesting. There is an additional material that we can use that's a little bit better than steel, and that can be made of diamond window tiles, potentially. Obviously, if we have a thermium floor, then that would be potentially even better. But for the sake of this, we are limiting ourselves to less than space age material. And I think those are all the ideas that would actually apply to a vacuum system like this on the left. So with all of that in mind, let's try to optimize this design. So first things we want to do here is try to get this iron to drop on the other side of the volcano, or I can just move everything here. But to do that, I can easily just do that number. So now when the volcano runs, it should just drop the iron over here. That will make the distance a whole lot shorter. Okay, so here's an interesting thing. Since I shortened this down, you can see that it goes up to a total of 530 watts right there, which means we are removing quite a bit more energy in a single cycle, which is going to cool down this iron faster. The question is it faster than our maxed out iron volcano? And we can see that the temperature right there is down to 136. So not quite. The volcano is, in this case, is just a little bit faster than what we're getting out of it. Now, it is kind of a moving target in that, the amount of mass that we keep building up over here is more and more and more. So An apples to apples comparison is going to be kind of impossible here, but we should be able to get some sort of understanding of what's happening. Okay, so I've added another door here. Let's see what happens with this. Now, this actually does give us a good apples to apples comparison. If I remove this, everything cools back down to the same temperature, 124 degrees Celsius here. So the next time this thing runs, if I let it run a couple times, we should see if the turbine can keep up with it now. There's more contact space here. So, and it is transferring. See how this is transferring to 2 tiles, not just 1? Because that door is right there. It's gonna bump that temperature up just a little bit faster. Look at that. We hit 680 watts. Or 690. Ooh! That's the biggest number I've seen yet. Ooh, 141 degrees. Okay. And now that there's more mass down here, the peak wattage that I was getting out of the steam turbine is less. See, the thing is, as we continue to add more and more mass right down here, the maximum temperature that this thing will ever get to is always going to be, that number is going to continue to drop down. Because it's, you know, you're only going to add a set amount, but the amount that's down here continues to go up. And because of that, the amount of heat, the amount of energy we're extracting from this is going to be reduced. So ideally, we want to get this to a point where we're cooling it down faster than we're adding to it, if we really want to make everything as cold as possible. Yeah, see, this one only ever went up, so it was like 650, 500 and something, and now we're less than that. We were at 480 or so. So that number keeps going down and down. Now, is this really a bad thing? Not necessarily if you're just using it for power, but what we're trying to do is make the refined metal useful. If this was just a volcano and all we're getting over here is igneous rock, it's not such a bad thing because this thing can just sit here and run a long, long time, and we can use the power as kind of a base load system throughout our base or whatever. So far, a shorter distance was an improvement. The additional door here was also an improvement. So let's continue with that same thought here. So we added this additional door here to increase the surface area that that it touches just for a moment there. And we also have more area here to transfer from this area up, right? So what happens if we add more metal tiles in this area? All right, let's see what the maximum temperature here is. Ooh, come on. 644, 650. Oh, we are almost up to, that was about 670 watts. Okay. Now there was one comment I kind of overlooked here from Bob Ross, and that was the different types of materials. We do have to investigate that. Now this also brings up another topic that was talked about by French Stud here, and that is thermal diffusivity of the actual material. Now this gets into the thermal conductivity and its heat capacity and how well the materials kind of transfer the heat from one to another. Now while we could get into equations and whatnot, let's just set up a practical example, shall we? Alright, so here's my little example here. From the left I have copper, iron, gold, tungsten, steel, diamond, and then thermium as well. So only one of these is space age, and that is this one over here. Now all of these have a combination between specific heat capacities and the thermal conductivities. So in this demonstration, what I'm going to do here is I'm just going to brush on one tile of molten iron just to see how this heat transfers down these long stems of the same type of material. Okay, so here's my test. I have iron up here, 20 kilograms of it at the molten temperature, and watch what happens. So you can see just how quickly the heat is transferring down these two materials right here. Now, what are these two materials? Well, they're gold, and they are also tungsten as well. These both have a low specific heat capacity with a relatively high thermal conductivity. If we take a look at my chart here, you can see that gold is actually going to be transferring between itself faster than any other material there. So it will balance its own temperature very, very quickly. The other thing to keep in mind, though, is by the time this gets to the bottom, what is the temperature of the iron at the top? Because that's ultimately how fast we're getting the energy out of what we want to get the energy out of, so that we can, you know, get rid of it, move it out of the system, and then use whatever conductivity we have down here to pump that into the steam. So this is a fairly complicated little thing, so we're going to have to kind of run this test a few times here just to kind of see what happens. So there we have it. You can see that this right down here is at 20.4 degrees Celsius, and that is 20.3. But what is the temperature at the top? So looking left to right here, above copper, you can see that this got down to 146 degrees Celsius. This one was 79.2. What was that material? That's iron, so iron to iron. So while the gold was able to transfer that heat all the way down here, let's take a look at the iron on top of that. That's still up there at 392 degrees Celsius. And the one over tungsten is up at 407. So the one above steel right here, check that out. So that is 71.1 degrees Celsius. So that is the lowest number we have seen yet. The one above diamond here, see, that is still up there at 712 degrees Celsius. Matter of fact, the one that's above thermium right there is up there at 1,839 degrees Celsius. It hasn't even turned to a solid yet. So steel is really sucking that energy out of that iron and putting it into itself. However, it's not transferring it very quickly along a very long distance here. This is interesting. Because at the same time while I'm doing this, I'm looking, okay, there was another comment over here that was talking about the maximum amount of mass that's calculated between the surface area of two objects. There's like science and video game science, and they're just like, what's going on? We're off the deep end. Okay, so now I need another experiment. So the real question here is, how fast does it go from the liquid through the metal tiles, materials, and into a body of water or steam? So here's what we're going to do. Aha! You're gonna like this one because it's practical. Boom. We're just gonna do this number and we're gonna see what one goes fastest. Okay, so this is getting cool. Here's what we got going on here. I have 1 kilogram of water down here, surrounded by the material that I want, and then the liquid iron is going to drop on top of here. So that's 20 kilograms at its molten temperature, and we're just gonna see which one heats up the fastest. So the key here is to look at the water, right? Interesting. This is really, really interesting. Okay, so if you look at the water, right, this one here is nearly at the temperature of steam, right? It just went over 100 degrees Celsius. However, the iron is still 389 degrees Celsius, or 403 over here. So what we can clearly see here is that the fastest way to heat up that water is obviously using the most thermally conductive with the least specific heat capacity. It's transferring the fastest. We can see that clearly right there. However, we're extracting energy from the iron faster by using our steel tiles, right? So this one up here is at 83.1. The next closest is 81.7. And these probably have very similar properties, right? 0.4, 49, and 55. And then 0.49 and 54, yeah. So pretty much both steel and iron are about the same. Which is cool because iron is actually a lot easier to get than steel. All right, so for the next step here, what I want to do is I want to try one of these setups, but using iron on top and then using gold to transfer that into the water to see if that makes a significant difference. Okay, so for this test, what I have is all of the original materials on top, but then it moves to gold down here below to see if we can get that energy out and then transferring a little bit faster. We'll see. Let's see what happens. So you can see that, ooh, yep. I don't know exactly what I'm seeing. But let's just pause it right here. Okay, so this one is on top of steel, which was, you know, we saw that that was the lowest temperature. So it's up at 202. That one is still quite hot. So we're definitely not getting the same results. Tungsten up top, gold beneath. The steam is up at 108, and that's the highest number I have. The temperature there is 391, and then 397. So a lot of the energy here is just going into heating up these, you know, the higher specific heat capacity tiles right there. That one right there is going into here. So in our setup, what's better? To transfer it faster or to balance it faster? Because we have to remove that heat per cycle. Okay, so what I'm seeing here is that there isn't like a great combination that I can see right now as far as, you know, this being steel and this being gold. That combination is not really leading to anything great. If anything, maybe tungsten up top and then gold down beneath is a little bit better, but you know what? It looks like gold all by itself is definitely going to transfer that really fast. However, it's going to have to be quite cold on the other end because we're just not sucking it out of that iron all that fast. So there's only one more thing to do here, and that is to A/B test this, right? So make everything out of steel, see how that reacts, then make everything out of gold and see how that reacts. Okay, there is one other thing we can do here to test this, and that is what if we use a temperature shift plate right here? So it's going to drive it into that metal tile. Now there is one more thing that we can test here, and that is if we use shift plates. Now in the last video I showed that when you have a shift plate in a liquid or a gas, then it's actually going to be in contact with each other. And we can use that to potentially drive the energy very quickly out of that liquid and solidify it. So that might actually allow us to transfer the heat much faster in a shorter amount of time. So let's go ahead and test that in the game here just to see how that would work out. So down here I'm just going to use gold temperature shift plates, and then up top it's all going to be just the exact same material that everything else is. So steel on steel, tungsten on tungsten, that sort of thing. I feel like we could just keep going and going on this, but all right, here we go. Let's take a look at what happens here. This is going to happen fast now. Boom! Look at that. Wow, okay, look at how similar everything is down here. Huh, and how different everything is up top. Wow, okay. I don't really know what to make of this right now. Okay, so these have just tipped over. Okay, these three here have tipped over 100 degrees Celsius. These are quite a bit closer. Now up top here, you can see that this really didn't, using the same material, right? So when we went to iron, that's still up over 1,000, which is crazy, actually. Because usually that was cooling down the fastest. Why in this situation did it not do that? But it did in the last setup. What? What? I don't understand. I mean, that almost refuses to drop in temperature. What? How? It isn't making contact with the tiles. What? If I deconstruct that? Huh? And then if I redrop it on there, look, it started to transfer again. I broke the game! Sorry, Clay! So what do I do now? It worked when it dropped, but it didn't work when it dropped and converted like at the exact same time. Put the temperature shift plate up higher. We're clearly into the video game, hackery science contraptions. Okay, I'm only going to do one more experiment because, let's face it, I'm kind of tired of setting this thing up. Okay, one last experiment here. This is all gold, this is all steel, this is gold here and here and here and here and here and here with steel right there. So the idea is that the liquid here in its form may hit the transfer shift plate, boom, throw a lot of energy out, and then become solid down here in the bottom. Let's see what happens. It may even still be a liquid pool, and it's still... See that? See? Okay, that iron, it turned to solid before it got through. Boom. And look at that. It's all the way down below 1,000 degrees, just like that. However, you can see the race to the water is still definitely being won out. Like, okay, this iron, are you kidding me? It's already down to 52 degrees Celsius. It's just chilling out. Like, we gotta just go with, like, I didn't even go through any time. That was it. But you can see the thermal mass here. The amount of mass that I have to work with is a lot more. So it just doesn't... And it isn't heating up that water as fast because there's just more mass. So what do you want to do, Brothgar? What do you want to do? That's up there to 120. Okay, first things first. 300, 120, 50 something. If we take a look at anything else... Okay, that one actually worked that time. Look, the temperature shift plate thing in the bucket design, it works. All right, so here we go. I'm just going to move this over here, and we're going to re-engineer this to take full advantage of the temperature shift plate magic drop. Okay, now iron pretty much worked just like steel. So for the sake of this, we're going to use iron because it's easier to obtain than steel. So iron, iron, iron... all the way around. But the problem is we only have steel doors. So, okay, so what I meant to say is that we're going to use all steel here because the doors have to be steel. Ha! So just like that, and then down here we're going to just use lots of steel doors. So the thing we're going to add here is a temperature shift plate right here, and see how that works with the iron volcano. So the hope is that as this runs, we're going to be able to get a really high amount of energy out of it. We may even be able to close the door. If we can close doors, wow, that'd be really good. All right, here we go. That's heating up from 125. And are seeing the maximum output at 600. It keeps going up. Topped out at 605. And the difference in the temperature between the two, well, the iron is actually catching up to what's inside the chamber quite quickly, actually. At this point, it's, what is it, like 30 degrees Celsius? Now we're only about 10 apart. That's not bad at all. You can get down to 150 C from over 2,000 in a single cycle there. That's not bad at all. Maybe it keeps going too. But it seems like the difference there hits about 7 degrees different. And that's not bad at all. However, the steam turbine is not consuming enough energy. The iron volcano is going to continue to heat everything up more and more. Now, what are the temperature shift plates inside of here? Those are made of steel. Okay, good. Yep. Interesting. Okay, so I'm going to replace everything here with gold. All right, so this is the opposite. We have a lot less thermal capacity, but we have a lot more conductivity. Okay, so this is the gold test here, and we can see just how hot things are getting in there and how much power are we generating. To 500, 600, yes. Even more. Yeah. Through the cycle, 350, 650. Ooh, are we gonna hit 700? No. We do hit 600 and just about 670 watts. You know what? And the difference in temperature between the iron and the thermal sensor, again, really isn't that bad. I'm only seeing like 20 degrees or so. However, you can see here once again that We didn't get back to 125 before the next cycle started. So that makes me think we need more heat over here on the right, which means we need less mass. So to do this, I'm just going to have a gold thermal shift plate right there. I'm just going to cut down the number of shift plates I have all together. There we go. I only have one there, and one up there. Less mass, because each one of those is pretty big. You see, they're 800 kilograms. All right, so here's the big test. Is this going to be fast enough? Come on now. Come on, Steam Turbine. Give me some sevens. Oh, you know what? It is fast enough. See, it shut off just before the end of the cycle. How about that? Or sorry, just before this thing started to erupt again. So it was fast enough to keep up with the iron volcano at least once. Let's see if I can repeat that. Yes. Yes, it did. And what temperature does that iron get down to this time? 140, 150 something? So if we sense the temperature of that iron, we could, and here's where things get really clever, open up a door and drop that iron down into a liquid lock where you can then pick it up. And because we can make that out of petroleum or crude oil, it won't turn to steam, so it's safe. So we can constantly cycle iron out of this unit while getting power out of it at a relatively safe temperature without the need of any space age materials. All right, so to do that, there's a couple of people that left this idea, and this is where you have the metal tiles right here with a little bit of water underneath it. And this sensor will give you an idea of how hot this stuff is while in a vacuum environment. The only thing is that I can't run gold down here. I have to run the steel door. I think where this is ending up is going to look a bit like this. Okay, so there was a problem. If I have the shift plate right there, that turns into iron right there, and I can't get it. And it's not doing any transferring at the moment, so I cannot have the shift plate right there. Maybe that was just a fluke. Maybe I could just go ahead and put that right there. Let's try it. Oh, look at that. That's some big numbers. So how this is set up is I have an automation. So if this here is at 356 degrees or above, ooh, hang on, that ain't right. You know what? We don't need this automation. That can just go away. If it gets that hot, it isn't going to matter. You have to, get rid of that extra energy anyhow. So we can just get rid of that. And rather just do that number right there. Of course, now I don't have a cool sensor to look at. You know what? We can make this a little bit more compact. If we do this. Ha. And that allows me to do that number right there. Cool. Okay, how did a Draco get up here? Where did you come from? This is completely in... You dug a hole, didn't you, Draco? Alright, anyhow. Heating up from a shutdown. Let's see how this does. Show me the watts, baby! Come on! 585? Lame! I'm gonna have to set this up to be a little weird. So that'll be like 130. And then at that point it drops down and things cool off. That just needs to be a signal, not a... Yeah, okay. More changes. So this should do it. Run this to a filter, to the memory toggle. Yeah, that is over the 600 mark, so that's pretty good. And in one complete cycle of this iron volcano, it looks like we're able to burn off all the energy it was able to put out. Ha! And then it drops down. Yes! And the little automation signal works. All it is just a filter next to a memory toggle. Boom! Take that. And what's the temperature of this down here? 138 degrees. Perfect. And here comes the next wave of iron. Beautiful. Now, if you're just trying to cool this stuff down, honestly, that's like all you need. You wouldn't really need all of these doors in there. However, if you're not, if you're disabling this for a little bit, you're going to build up that temperature. But the thing is, it's not going to drop that out because it's just too hot. See? It's not dropping it. Not a big deal. This thing will erupt again in a few cycles. Maybe I re-enable it. Look at that power. Boom. Pumping out into the base. Doing all sorts of fun stuff. Maybe my base is full of light bulbs. I don't know. Probably running ice maker machines, really. So there we have it. It was disabled for a little while, but now this power is going up even higher, right? We're up to 680. But we filled up our batteries. We'll disable it. Alright, so this volcano is going to run again, but we're still not using the steam turbine. This is just a very efficient... Oh, look at the doors! They're starting to do their thing. Starting to do their thing. Ooh, there we go. Look at that. 800 watts! But the door isn't quite there. Watch what happens when we go beneath that. Boom! 850 watts! Automated. Efficient. I love it. It's dropping right down from that 850 mark. Ha! Alright, so let's just clean up the design here because you know what? This works. Make it a blueprint-ish thing. Okay, so one of the cool things here is that we can use an auto sweeper and even a conveyor loader as well to kind of pick that up and move it around, or just use a simple liquid lock like this, and once it's done, it'll just drop right down here and you can just pick it up. Now this will bring a little heat out here, but I don't think that's a big deal. The same thing is going to happen over here as well. I like it. I really do like it. Alright, so check it out. See? Iron Volcano is running. We're generating power. That power is just going and running into the base. There we go. Now we got some power. Sweet. We're trying to knock down the temperature on this thing. By the way, I've set this to 130 degrees Celsius. All the tiles here are made of gold, and except for the one steel door that we have. You know how that's set up now, so that's not a big deal. Below 225, below 200, below 269. This here is not necessary. One potential thing that we could potentially do here is just reduce the amount of steam in this area. That was set to 1,000 kilograms. Maybe less. I mean, might be able to generate more heat, but at this point I think I've tested more than enough stuff. And boom, there we have it. The iron drops down, and now it's ready to be swept up. So if I hit sweep, the dupes should come on over there and pick it up. And this thing's ready to go for another round. And in that previous cycle, the steam turbine generated 297 kilojoules. 150 before that, 326. So not huge numbers, but considering this is renewable energy, then there we have it. It's just kind of there, ready to be tapped into, and we can pick up iron and make it nice and useful. That's so cool. I love that. That's so fun. Here, we'll just use a little chute, just like that. Check that out. This will be for refined metal. And if I do this number, we'll see it work. Okay, so what happens when we throw a giant volcano at it? At its maximum production rate, mind you, this is like the biggest volcano you can find. I'll have you know this thing doesn't really erupt all that often. So it's probably going to erupt quite a bit of material. And its average output is 1,897 grams a second. Alright, so here we go. Normal speed. In 3, 2, 1. It's volcano time. That is a lot of material. Oh, look at all of that. What? Uh-oh. And how's the temperature shift doing here? Well, it's trying to get there. Oh no! Too much material! Oh no! Oh no! It melted the gold! Oh! Wow. Wow. It's still going, by the way. 467 kilograms a second. As you can see, the steam turbine is starting to shut down its doors here just to try to survive. That's a lot of magma. Okay, well, it didn't keep up with that. Oh yeah, and we're definitely getting 850 watts. Okay. No, it's actually well above. At this point, we're just trying to delete heat. Oh no! Oh no! Things are not going as planned. Too much heat. All right, well, I guess we'll have to do something a little bit different to deal with a ginormous volcano. If you ever even find a ginormous volcano like that. Like, when's the last time you've actually seen that? I can't remember the last time I've seen a maxed out giant volcano. However, for something like this, it might be a whole lot better to have an enclosed system, which is what we're going to cover next time. At any rate, that's all I got time for today. This was a pretty big episode, took a long time to record, and I'm looking forward to the next one. Thank you guys for watching. Hopefully you guys have enjoyed this episode. A big shout out and thank you to my Patreon supporters. You guys are absolutely awesome for helping me out through this time of transition and everything else that I got going on here. A lot of big things have happened, but they've all happened in the background this month. So thank you guys for your support. Have a wonderful day, guys. Thanks for watching. I'll see you again next time. Stay awesome. Peace. Brothgar out. There's a new Humble Bundle from Full Stack Web Development. These are video training courses that'll get you up and running in things like HTML, CSS, JavaScript, and a whole lot more if you take a look at everything that's down there. This bundle is laid out in a very logical way in that you get intro classes, intermediate classes, and then the more experienced ones, and each one leads into the next. How these training courses work is they're a video course that kind of plays out like this in short little bits where they show you what's going on and explain what's happening, and you can follow along just like this and what I'm doing here. But it also has a complete write-out down below each lesson that explains in detail what's happening there if you're more of a visual learner. For me, this is the type of training course that actually gets me to do something. I'm not so great with books, but videos, I can do that. If this looks interesting to you, then go ahead and check it out using the link in the description below. I'm partnered with Humble Bundle, so not only will your purchase go to help support these great charities such as V Foundation, World Wildlife Fund, or in my case, the St. Jude's Children's Research Hospital, and it'll also go to help support this channel. There's several different tiers available, or you can pay what you want. Thank you guys so much for your support, and have a wonderful day.